Hello student, in this video lecture I am going to explain the geometric distribution. First we see the concept of geometric distribution, then probability mass function of geometric distribution. Okay, now the concept of geometric distribution is that suppose a coin is tossed till a head occurs for the first time. Then the head may be occur at the first trial or second trial or third trial and so on. Then let capital X be a number of failures before getting a head in a single trial. Capital X, this is the random variable, and this random variable is what? The number of failures before getting the first success. Means we consider the experiment of tossing a coin. In that case, this X denote the number of failures before getting a head for the first time. Now we have to obtain the probability distribution of the discrete random variable X. Then the number of now suppose this P is the probability of success and Q is the probability of failure. Means here P represent the probability of getting a head and this Q represent the probability of getting a tail, and P plus Q is equal to 1, that is total probability is equal to 1. P lies between 0 and 1. Okay, then in this case the trials are independent, or assuming that trials are independent. Now the probability distribution of random variable X will be, that is random variable X takes values 0, 1, 2, 3, dash 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 X, again dash dash dash, with corresponding probabilities are, that is P of X is equal to, probability at X equal to 0 is P, then probability at X equal to 1 is Q into P, here is Q square into P, Q cube into P, dash dash dash, here is Q raised to X into P, again so on. And this is the probability distribution of geometric distribution with parameter P. Since these probabilities are in the geometric progression, therefore this is called as the geometric distribution. The geometric distribution is used in reliability and queuing theory. Now we see the probability mass function of geometric distribution. This is the probability distribution of geometric distribution. Now PMF, or probability mass function of geometric distribution. PMF, that is probability mass function. Okay, now consider a Bernoulli trial. Consider a Bernoulli trial with constant probability P of success in a single trial. Okay, that is, Bernoulli trial has only two outcomes, out of which one is success, other is failure, and this P is the probability of success in a single trial. Now suppose we have a X number of failures before getting the first success. That is, number of failures before getting first success is X. There are X failures before getting first success. Then in X plus 1th trial, or result of this trial is into the success, means we get success at X plus 1th trial. Then the sequence of this experiment is, that is, there are X failures F dash 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 F, and in the X plus 1th trial result is success. This is X trials, okay, and this one is the X plus 1th trial, X plus 1th trial. Okay, then we know that the probability of failure is equal to Q, that is the multiplication of Q X times, or X times multiplication of Q, and here is a success. S stands for success, F stands for failure, and we have a success at X plus 1th trial, and the probability of success is P. Okay, now the probability of X failures is equal to Q raised to X, and probability of success is P. Okay, then the probability mass function of geometric distribution is, or probability of random variable X is, random variable X is, here is what, number of failures before getting a first success, that is probability of X equal to small x, which is equal to Q raised to X into P. Here X takes values 0, 1, 2 dash 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 up to infinity, 0 otherwise, 0 otherwise. This is the probability mass function of geometric distribution. Okay, now the notation of geometric distribution is that this random variable X follows geometric distribution with parameter P. This is the notation. X follows geometric distribution with parameter P. G stands for geometric, P is the parameter of the geometric distribution. We use this notation. This can be read as X follows geometric distribution with parameter P. Okay, now the support of geometric distribution is, support of geometric distribution is 0, 1, 2 dash dash dash, that is 0 to infinity is the support of geometric distribution, and the parameter space is what, P given 0 less than P less than 1. Okay, now we see the another form of geometric distribution, another form of PMF of geometric distribution. Okay, now suppose this let Y denote the number of trials required to get the first success. This Y is what? Number of trials required to get the first success. Then Y is equal to x plus 1. Okay. Now the probability mass function of Y is probability of Y is equal to small y is equal to q raised to y minus 1 into p. Here y takes values from 1, 2, 3 dash 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 and 0 otherwise. This is the another form of the geometric distribution, which is also called as the waiting time distribution. Here y takes values from 1 to infinity, okay, and in the first form the random variable x takes values from 0 to infinity. Okay, now we verify that the second condition of the probability mass function, that is summation of p of x is equal to 1. Summation of probability of x equal to small x, summation over x, which is equal to summation of q raised to x into p, summation over x, x running from 0 to infinity. P is constant, take out of summation sign, then summation of q raised to x, summation over x, x running from 0 to infinity, again which is equal to p into in bracket, put x equal to 0, then we have 1 plus, put 1, q plus q square plus q cube plus dash dash dash, bracket complete. Then the sum of this series is equal to what? Which is equal to p into in bracket 1 minus q bracket raised to minus 1. The sum of this series is equal to 1 minus q bracket raised to minus 1. Then we know that p into q raised to minus 1. Since p plus q is equal to 1, therefore p is equal to 1 minus q, that is 1 minus q is equal to p. Okay, then the which is equal to p upon 1 minus q, which is equal to p upon p, which is equal to 1. That is the total probability is equal to 1, means the geometric distribution satisfy the second condition of probability mass function. Okay, now we see the mean and variance of geometric distribution. Mean and variance of geometric distribution. First we derive the mean of geometric distribution. Mean, okay, that is expected value of random variable x is equal to summation of x into probability of x equal to small x, summation over x. Now substitute here probability mass function of geometric distribution, which is equal to summation of x into q raised to x into p summation over x running from 0 to infinity. And here p is the constant, take out of summation sign, p into in bracket write down here p into summation of x into q raised to x summation over x running from 0 to infinity. Now put x equal to 0, x equal to 1, x equal to 2, then we have a one series which is equal to p into in bracket. If we substitute x equal to 0, in that case the value is 0, plus now put x equal to 1, then the value is q. Next one is 2 into q square plus 3 into q cube plus so on, that is dash 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 dash. Okay, now this can be written as p into in bracket q plus 2 into q square plus 3 into q cube plus dash dash dash, bracket complete. Now take q common from each term, then we have p into q into in bracket 1 plus 2 into q plus 3 into q square plus 4 into q cube plus dash dash dash, bracket complete. Now the sum of this series is p into q into in bracket 1 minus q bracket raised to minus 2. The sum of this series is equal to 1 minus q bracket raised to minus 2, which is equal to p into q upon p square. 1 minus q is equal to p raised to minus 2, this can be written as 1 upon p square. Now p gets cancelled, we have q upon p. Q upon p is the mean of geometric distribution, or it is the expected value of random variable x, and that random variable follows the geometric distribution, which is equal to q upon p. Now we find variance of geometric distribution. Variance of geometric distribution. By definition of variance of random variable x is equal to expected value of x square minus expectation of x its whole square. This is the definition of variance. Now first we obtain the expected value of x square, and we know that expectation of random variable x is equal to q upon p, this one. Okay, now consider expected value of x square. Now this x square can be written as x square minus x plus x, means in x square we subtract x and we add x, the x square remains the same. Now from the first two terms, expectation of x into in bracket x minus 1, this plus x is as it is. From these two terms we take x common. Okay, now again this can be written as expected value of x into in bracket x minus 1 bracket complete plus expectation of x. This is the expected value of x square. Okay. Now we first obtain the expectation of x into in bracket x minus 1 as follows. Okay. Then we know that expectation of random variable x is equal to q upon p. Okay. Then by definition of expectation, we have summation of x into probability of x equal to small x, which is equal to q upon p. Here is summation over x. Now substitute here probability mass function of geometric distribution. Then we have summation of x into q raised to x into p, summation over x running from 0 to infinity, which is equal to q upon p. Okay. Then by making some adjustment, this equation is equal to what? We have this one is equal to summation of x into q raised to x minus 1, which is equal to 1 upon p square. Okay, means we transfer this term q to the left hand side and this term p to the right hand side. Then we have summation of x into q raised to x minus 1, which is equal to 1 upon p square. Here is summation over x running from 0 to infinity. Okay. Now again this can be written as, this is equal to 1 upon 1 minus q bracket raised to 2, which is equal to 1 minus q bracket raised to minus 2. That is p is equal to 1 minus q. We substitute here 1 minus q in place of the p. Okay. Now we differentiate this equation with respect to the q. Okay. Now we differentiate this one. This is equal to summation of x into in bracket x minus 1 into q raised to x minus 2, summation over x running from here is 1 to infinity, which is equal to derivative of this term is equal to what? Minus 2 into derivative of this term is 1 upon, that is 1 minus q bracket raised to 3 into derivative of minus q is minus 1. Okay, which is equal to again 2 upon 1 minus q bracket raised to 3. That is summation of x into in bracket x minus 1 into q raised to x minus 2 is equal to 2 upon 1 minus q bracket raised to 3. Now we divide q square into p on both sides of this equation. Then we have, by dividing q square into p, we have summation of x into in bracket x minus 1 into q raised to x minus 2 summation over x, this divided by q square into p, which is equal to 2 upon 1 minus q bracket raised to 3 into q square into P. That is, we here instead of dividing we multiply this term, then we have, if we multiply, that is 2 upon 1 minus q bracket raised to 3, then here is q square into p and q square into p. Instead of dividing, we multiply on both sides of this equation by q square into p. Then this q square gets cancelled. Okay, then we have summation of x in bracket x minus 1 into q raised to x into p summation over x, which is equal to, this is 2 upon 1 minus q, that is p cube into q square into p. P gets cancelled, then we have 2 into q square upon p square. Okay, and this is equal to what? This is the expected value of x into in bracket x minus 1, which is equal to 2 into q square upon p square. Sorry. Now substitute this value in the equation of expected value of x square. Now expected value of x square becomes, expectation of x square is equal to expected value of x into in bracket x minus 1, which is equal to 2 into q square upon p square plus expectation of x, that is plus q upon p. This is the expected value of random variable x. Now we obtain the variance of random variable x. Variance of random variable x is equal to expectation of x square. This is the expected value of x square, that is 2 into q square upon p square plus q upon p minus expectation of x its whole square, that is q square upon p square. Okay, here is 2 times q square upon p square and here is minus q square upon p square. Then we have only q square upon p square plus q upon p. Now simplify this. First we make the denominator of these two terms equal to same. Then we have, this is q square plus p into q upon p square. Okay, now take q common. If we take q common from both terms, then we have q into in bracket q plus p, okay, upon p square. We know that total probability is equal to 1, that is p plus q is equal to 1. This term is equal to 1. Then we have variance of random variable x is equal to q upon p square. This is the variance of random variable x since q plus p is equal to 1. Okay, this is the variance of geometric distribution with parameter p, which is equal to q upon p square, and mean of geometric distribution is q upon p. Okay, thank you.